Hello friends, so today we are going to solve the question from rotational motion, and these questions are from the year 2022, and we are going to solve 6 questions, and all these 6 questions are from the mains only. And for the year 2022, this is part 2. In the part 1 we have already covered 10 questions, and those 10 questions were also from the mains part. So the first question: a solid cylinder and a solid sphere having same mass m and radius r roll down same identical plane from top without slipping. They start from rest. The ratio of velocity of the solid cylinder to that of solid sphere with which they reach ground will be. So in this case, it is basically, you can say, about the conservation of energy, and as the motion is without slipping, so it means it is a pure rolling. So we are going to have two types of kinetic energy. One will be translational and other one will be rotational. So we can just draw an approximate figure for that. So initially we suppose that the solid cylinder and sphere are somewhere here, and they are at a height h, okay, and they start from point A, and ultimately we have to find out what will be the ratio of velocity at the base, that is point B. So it means at point A, both solid cylinder as well as solid sphere is going to have same potential energy, that will be mgh. So you can say potential energy at point A for solid cylinder will be also mgh, and solid sphere will be also mgh. Okay. And at the bottom, that is at point B, so you can say at bottom, which is point B, total kinetic energy let us suppose we call this as Ke total, and we can write that this Ke total will be equal to kinetic energy translational plus kinetic energy rotational, and we can substitute the respective formulas. Our translational will be over half mv square plus rotational will be over half I omega square, and the motion is pure rotation, or we can say no slipping. So therefore we can write that our V is equal to omega times R, okay, where because it is going to in this direction, it is going to angular, you can say velocity will be omega, and the linear velocity will be over V. And we already know, we can just, because we are interested here in this I, which is the moment of inertia. So for the solid sphere, the moment of inertia will be different, and for solid cylinder, the moment of inertia will be different. Okay. So let's start with our solid sphere. So you can say for solid sphere, moment of inertia, that is Is, S stands for sphere, is equal to our 2 by 5 mr square. And we can modify the equation for our total kinetic energy, and we can write this as kinetic energy total, and this is particular for the sphere, will be equal to our half m velocity of sphere plus half, this is our 2 by 5, and we have this is mr square, and in place of omega we can write as velocity of sphere divided by radius of sphere and its whole square. So here this 2 goes with 2, and this square is going to cancel the square of the r. So we will get this as our half m vs square plus 1 by 5 m vs square. This can be, LCM will be about 10, so this becomes as 7 by 10 m vs square. So this is basically our kinetic energy of total of solid sphere. Now we can equate this with our potential energy according to conservation of energy. So you can say our conservation of energy, we get total kinetic energy 7 upon 10 m vs square is equal to our mgh, and our m and m cancels out. So from here we can write that our solid sphere velocity square will be equal to 10 by 7 times gh. Now same we can do it for our solid cylinder. So you can say for solid cylinder, moment of inertia is suppose IC, and IC will be our half m r square. Okay. Therefore we can say kinetic energy total of solid cylinder will be equal to half m velocity of solid cylinder, and this comes as our half 1 by 2 mr square, and this comes a velocity of cylinder divided by r, and this comes whole square. And here also this square cancel with this r square, and we are left with our 1 by 2 m v square plus this comes as 1 by 4 m vc square, and 4 will be our LCM, so this comes as our 3 by 4 m vc square, and this is our kinetic energy total for the cylinder. Once again, according to conservation energy, conservation of energy, we can write 3 by 4 m vc square is equal to our m gh. mass and mass cancels out, so we get our Vc square will be equal to 4 by 3 GH. Now we only required our, you can say, ratio. So we can say the ratio, which is our solid cylinder to solid sphere. So we have our Vc upon Vs will be equal to, and this comes as our 4 by 3 GH, and this is 10 by 7 GH, and this is our whole square. So GH and GH cancels out. This comes as 4 by 3 multiplied by 10, and this comes as 7. So this goes by 2 and this goes by 5. So this comes as 14 upon 15. Therefore, Vc upon Vs will be equal to square root of 14 upon 15. Therefore, the option number D is correct. Next question. It states that a disc of mass 1 kg, radius r, is free to rotate about a horizontal axis passing through its center and perpendicular to the plane of disc. A body of same mass as that of disc is fixed at the highest point of the disc. Now the system is released. When the body comes to the lowest position, its angular speed will be 4 square root of x upon 3r radian per second, where x is taking g as 10 meter per second square. So in this case, we can draw an approximate figure, and we are having a disc is free to rotate about a horizontal axis passing through the center. Okay. So we are having a axis, disc, and there is a horizontal axis, something like this. And it is free to rotate, let us suppose, in this direction with angular velocity omega. Okay. And r is its radius. Let us suppose mass is given as small m, which is 1 kg. Now in the second case, we are given that same mass is fixed at the highest point of the disc. Okay, so we have a mass which is fixed at the highest point of the disc, and this disc is free to rotate in this direction. So when the system releases this point mass, let us suppose we call this as point P, and its mass is given also as small m, and after rotation this point becomes at the lowest end. Okay, so under this condition, we are having our point mass is at the lowest point. Okay, and rotating with the angular speed of omega. Okay. So at this position, the angular speed is given. Okay, we have to find out what will be its value of x. Okay, the expression is given to us. Okay. So in this case, we are mainly interested in these two figures. Okay, so let me draw them again, or here also let us say that this is our center O, and on the upward side let us assume that this is a positive of R. Okay, and the lower side we can just make a reverse of it. So this we are calling as initial, and this we are calling as final. So we can say the initial status we are first of all interested in the position of this body, which we are called as P. So we can say position. So we can say the body, here we have called this as P, is at the highest point. Highest point. Okay. And we can say at height plus R above the disk center or axis, plus R above disk center, or which we can also call as axis. So at this particular moment we are going to find out its potential energy. And we know that the disk center of mass is at its axis. Okay. It basically means that if we are taking the our disk, so for this entire disk we can make a presumption that its entire center of mass will be at its axis, somewhere here. We can presume it. Okay. Therefore, even if the disk is going to rotate, its potential energy is going to remain constant. It's not going to change, okay, with respect to the center of mass. So we can say that the disk center of mass is at its axis, is at the axis, so its potential energy remains constant. But the body rotates, okay, so relative to the axis, and we can say that the body's potential energy relative to the axis we can call this at U initial. U initial will be equal to over mgr, and mass is a 1, g is our 10, radius is our r, so this comes as our 10 times r. And kinetic energy, initially it was at rest, therefore we can say that kinetic energy, we can say our system is at rest, which basically means omega is equal to 0, therefore our K initial will be equal to 0. Thus we can write that our total initial energy that is our E initial will be equal to U initial plus kinetic energy initial, and this comes as 10R plus 0, which gives us that our initial energy, total energy, initial energy is equal to our 10 times R. Okay. Now we come to the final state when it has rotated. Come to our final state, and we are going to make same analysis. First is our position. So the body is at the lowest point. Or we can say at height, which we are going to call minus of R relative to the axis. And the potential energy. So first of all, we are going to find out the body's potential energy. Body's potential energy, which is basically final, so we can say U final will be equal to our mg minus of R, and this will be coming as minus 10 times R. And now we come to the kinetic energy, and in this case also, like I said, that the potential energy is going to remain constant for the disk, okay, because with respect to the axis. Okay, so we are mainly interested in now in kinetic energy. So we can say the kinetic energy, and both the disk and body rotate together with angular speed omega. So moment of inertia will be into the picture, and therefore we can write that moment of inertia for disk, and let us call this as ID, will be equal to over half m r square, and mass is of 1 kg, so this comes as a half r square. And then we are having the moment of inertia for the body, and the body is a point mass at a distance r from the axis. Okay. So we can use the standard formula that moment of inertia of the body will be equal to mr square, which comes as r square. Therefore, total moment of inertia let us call this as I total, will be equal to disk plus body, and this comes as half r square plus r square, giving us 3/2 r square. And now we can easily find out its rotational kinetic energy, which will be our final kinetic energy. Therefore, we can say rotational kinetic energy, which is our K final, will be equal to our half total moment of inertia and omega square, and this comes as our half 3/2 r square and omega square. So we get our K final will be equal to 3/4, and we have this as r square omega square. Therefore, total final energy let us call this EF, will be equal to our potential energy final plus kinetic energy final, and this comes as minus 10 of r plus 3/4 r square omega square. And now we can use easily our conservation of energy. Conservation of energy, we can write our total initial energy is equal to total final energy. Thus we can write that our 10 of r is equal to minus 10 of r plus 3/4 r square omega square. Now it is a simple calculation. From here we get this will be our 20r will be equal to 3/4 r square omega square, and this r and this square goes away, and we get that our omega will be equal to, this will be our 80 divided by 3 and 3r rather, and its square root, and we are given that our omega is 4x upon 3r, and this is given to us as 4 square root of x upon 3r, and we can just manipulate it. We can write our 80, it can be written as 60 multiplied by our 5 divided by 3r its square root, which we can be written as 4, and now this comes as 5 3r, and which is equal to our the given equation x upon 3r. So this comparison gives us that the value of x is equal to 5. So we are having value of x is equal to 5. Next question. It states that the radius of gyration of a cylindrical rod about an axis of rotation perpendicular to its length and passing through its center will be dash meter, given that length of the rod is 10 square root of 3 meters. So in this case it is quite simple. We have a rod and its length is given as 10 square root of 3 and it is rotating about the axis which is passing through the center, something like this. And we have to find out the radius of gyration, and that formula is a standard one. We can say that our radius of gyration which is represented as small k will be equal to square root of moment of inertia divided by the mass m, and it is rotating about the axis which is passing through the center. Therefore we can say the moment of inertia will be equal to our 1 by 12 ml square, and therefore we can say that the radius of gyration k will be equal to, this comes as m, and we have 1.12 ml square. Here mass and mass cancels out. This comes as, we can take L outside, and this comes as square root of 12, which can be written as L and 2 root 3. L is given to us, so we can say the radius of gyration k is equal to 10 root 3 divided by 2 root 3. Root 3 and 10 goes by 5. Therefore we can say that radius of gyration is equal to 5. So that will be 5 meters. Next question. It states that a pulley of radius 1.5 meter is rotated about its axis by a force F, which is 12t minus 3t square Newton, applied tangentially, while t is measured in seconds. If the moment of inertia of the pulley about its axis of rotation is 4.5 kg meter square, the number of rotations made by the pulley before its direction of motion is reversed will be k upon pi. The value of k is. So here we are having a pulley and force is applied tangentially, and first time if you assume that it is moving towards the right side, then its reverse motion will toward the left side. And here we have to keep in mind one important point, that is our reversal of the motion, or reversal of motion. And this reversal of motion basically means when angular velocity will be equal to 0, then the reversal of the motion is going to take place. This is basically, we can just also relate it with the body which is thrown upward. If we take the direction upward going is positive, then at the highest point, just before it reverses its direction, that is coming back to the ground, momentarily it stops. At that moment the velocity becomes equal to 0. So this is also the reversal of the motion. Okay. So we can see the reversal of the motion. This occurs when angular velocity which is of omega is equal to 0. So obviously the force is tangential, so there will be a torque and that will be resulting in an angular acceleration. So let us first of all find out the torque and the angular acceleration. Torque and angular acceleration, and torque will be our tau. So we can say our tau is equal to our Fr, and which comes as our 12t minus 3t square, and radius is given to us 1.5. This comes as our 18t minus 4.5 t square. Now we can easily find out our angular acceleration from here. So we can say our angular acceleration, which is our alpha, will be equal to tau upon the moment of inertia, that is our I. Tau is our 18t minus 4.5 t square, and moment of inertia is given to us, about the axis is 4.5. So this comes as our 4t minus t square, okay, radian per meter square. From here we can find out our angular velocity. Angular velocity, and we know that our angular acceleration is equal to our derivative of our angular velocity, okay. And angular acceleration is our 4t minus t square. Okay. So obviously we can write that our omega will be equal to integration of 4t minus t square times dt, and this comes as our 4t square upon 2 minus t cube upon 3 plus c, and here this 4 goes by 2, so we are left with this as 2t square minus t cube by 3 plus c, and initially it was at rest, therefore we can say that our omega naught at 0 is equal to 0, therefore our this constant c will be equal to 0, and therefore we can write our omega is equal to 2t square minus t cube upon 3. Now, like I said, that the time reversal means omega is equal to 0. So we can say our time reversal is omega is equal to 0. So we substitute, we get this as 2t square minus t cube by 3 is equal to 0. And we can take this t square as common. We get this as 2 minus t upon 3 is equal to 0. So obviously this t cannot be equal to 0. So only the second term will be equal to 0. So we can say minus t upon 3 is equal to 0, giving us t is equal to 6 seconds. And we have to find out number of rotation. So we have found out that after time t equals 6 seconds, the direction will be reversed. Now we can just find out the angular displacement, and from there we can find out the number of turns. So we can see our angular displacement. And that angular displacement is, let us suppose that is our theta, and this theta is going to start with from t is equal to 0 and up till t is equal to 6 seconds. And we know that our omega is equal to d theta upon dt, and omega we already know is our 2t square minus t cube by 3. And we can write from here that our theta will be equal to the integral of 2t square minus t cube by 3 times dt. And we get our theta will be equal to our 2t cube upon 3 minus t4 divided by 12 and plus c. And once again, initially the angle was 0 at t is equal to 0. Therefore, we can say our c will be equal to 0, giving us that our theta will be equal to 2 by 3 t cube minus t4 by 12. This is our angular. And we can find out that our this at t is equal to 6 seconds, we can find out what will be our theta. Okay. So we can say at t is equal to 6 seconds, we can say our theta will be equal to 2 by 3 6 cube minus 6/4 divided by 12, and this will be equal to our 144 minus 108, which gives us that our theta is our 36 radians. So the angular rotation with respect to theta is our 36 rotation. Now we can just find out the number of rotations. So we can say that our number of rotations, let us suppose they are given as capital N, then we know that one rotation is our 2 pi radians. So we can say this N will be equal to theta upon 2 pi, and theta is our 36 and this is our 2 pi, giving us 18 upon pi. And we are given this is equal to k upon our pi. Therefore, the value of k is our 18. Value of k is 18. Next question. it states that as shown in the figure, a metallic rod of linear density 0.45 kg per meter is lying horizontal on a smooth inclined plane which makes an angle of 45 with the horizontal. The minimum current flowing in the rod required to keep it stationary when 0.15 Tesla magnetic field is acting on it in a vertical upward direction will be. So we have to find the current in the rod. So this is our rod, so that the rod is stationary, which basically means all the forces acting on the rod should be balancing each other, and the forces will be because of mg and because of the magnetic field. Okay. And we can just draw the approximate. So first of all, let's forces on the rod. We can say that forces on the rod and first will be the gravitational force, or rather we can say gravitational force component. So first will be our gravitational force component. Force component. Okay. And so first of all, let's find out what will be the gravitational force, then we can easily find out its component. Okay. So we can say that, because let me draw the figure also. So from the side, if you look, the rod will be something like this. Okay. And there will be a component which is our gravitational force. Let us call this as Fg, which will be nothing but our mg. And the angle, let us suppose, is given as theta. So we can divide this into two components, down the inclined plane and perpendicular to inclined plane. So this will have theta. So we are going to have mg cos of theta, and we are going to have mg sine of theta. And for the motion, it is moving in the downward direction, so we are only interested in this mg sine of theta. Okay. So the gravitational force component, we can write this, we can call this as our Fg, and we can call this as a parallel component to the inclined plane. Okay. And this Fg parallel component will be equal to our mg sine of theta, and we have this as, okay, we need to find out the mass, and mass will be equal to our, let me calculate it. So m is the mass, and this mass will be our charge, the what is given, linear density multiplied by length. Suppose length is L, so this comes as our 0.45 times L. So we get this as our 4.5 times L, and G is said to be taken as 10, and we have this as sine of 45. So we get that the gravitational force component parallel to the inclined plane is equal to our 2.25 square root of 2 times L. Second force will be our magnetic force. Okay. Magnetic force. And So the magnetic force, let us suppose we call this as a Fp. Then the general formula of Fp is our current, and we have this unit our vectored form of a length and the cross product with the magnetic field. Okay, and so in this case we can also divide our magnetic field force, and so this is our rod and the magnetic field force Fp, and we can divide this into two components. This will be our parallel to the inclined plane and horizontal perpendicular to the inclined plane. Okay, and we are going to have this will be our angle of 45. So we get this as Fp and cos of 45, and this will be our Fp sine of 45. Okay. So we are only interested in our this horizontal component, which is basically parallel to the inclined plane. So we can also find out this Fp using vector notation also. Okay, let me try that. This is quite simple otherwise. Okay, we can just balance it, but let us, you can say, use the vectored approach and find out the our magnetic field and then the force. Okay, so we are interested in this magnetic field, therefore we can say that magnetic field B will be equal to, its magnitude is given to us as 0.15. Two components, we are going to have cos of 45, and let us put this over I unit vector plus sine of 45, and this will be our k unit vector. Okay, and yeah, so this can be written as, this will be 0.15 square root of 2 divided by 2, and this comes as our I unit vector plus k unit vector. And now we come to our this L vector, that's a length vector, which is our rod. So we can say our rod along y-axis we are going to have this L vector can be written as L j unit vector, and similarly we can write the current. Current is our, in the figure it is already given to us, that is it is along j unit vector, therefore we can say our I will be equal to I j unit vector. Now we can easily find out our magnetic force, that is a Fp. So we can say Fp is equal to I, and this comes as L j unit vector cross, and magnetic field we found out is our 0.15 square root of 2, and this comes as 2I plus k unit vector. And this is now quite simple. We can write this will be equal to our, and we are magnitude will be our 0.15 square root of 2 divided by 2, and this comes as I times L, and we are going to have j cross I, which is our I unit vector, and we are going to have j cross k, which will be our minus of k unit vector. And this magnetic field is we can say that the component along incline, which we have taken as x-axis, and in the upward direction we know that it is our minus I unit vector. Therefore we can write our magnetic field in x direction will be equal to our, and this comes as our 0.15 square root of 2, and we have this as I of L and minus I unit vector, and the magnitude we can say that we are going to have this as equal to minus 0.15 square root of 2 upon 2 and I of L. Okay, and this we are going to get the same with respect to this also. It will be same, but here just a vectored notation, a different kind of approach. And our magnetic field, the gravitational force we already know. So let me write it, that the gravitational force which is down the inclined plane which is above plus of I. Therefore we can write that f of g parallel component is our 2.25 square root of 2 times L, and at equilibrium their summation will be equal to 0. So we can say for equilibrium we have our fpx plus fg parallel will be equal to 0. So we simply substitute it, we get this as minus 0.15 square root of 2 divided by 2 IL plus 2.25 square root of 2 and L is equal to 0. So obviously length cannot be equal to 0, so we can just ignore it. So we can write our current I will be equal to, this comes as our 2.25 square root of 2, and this comes as multiplied by 2 and divided by 0.15 square root of 2, and square root of 2 cancels out, and this comes as our 4.5 divided by 0.15, which is our 30 amperes. So option number A is correct. Next question. It states that the torque of force 5I plus 3J minus 7K about the origin is tau. If the force acts on a particle whose position vector is, okay, I have repeated this, whose position vector is 2I plus 2J plus K, then the value of tau will be. So this is quite straightforward. Torque is cross product of position vector as well as the force. So we can say that our torque, which is our tau, is our position vector cross force. Okay. And we can write that our R cross F will be equal to, this is our I, J and K, which gives us R is our 2, 2, 1, and this is our 5, 3 minus 7. So first time it's called as 14, 14 minus of 3, giving us minus of 17. This comes as minus of 17I, and we have minus, and this comes as our 14, 14 minus 5, that is our 19, minus minus will be our plus. So this comes as plus of 19J, and K will be equal to our 326 minus 10, that is minus of 4, minus of 4 K unit vector. So we get 17 plus 19 minus 4. Option C is correct. Option C is correct. So this completes all the questions for the year 2022 means. We did it in two parts. In the first part we solved 10 questions, and this second part we solved 6 questions. Advanced question we have already done in the previous. So this completes the 2022. Thank you.